Good morning, everybody. Welcome. It's my great pleasure to introduce this morning Dr. Ralph Weischedel. Ralph is principal scientist at BBN, where he's been for many years, and he directs a group of about 25 researchers there doing all manner of human language technologies. He is widely published in the field in not only information extraction, but parsing, speech, you name it. He and his group have worked on it. And you've all read many of his papers before. And today, Ralph will be talking about information extraction.
Well, good morning. I think the ground rules ought to be, since I really don't know most of you at all, and I don't know where you are in your background or interests, that you interrupt with questions at any time, as opposed to trying to save them up to the end and forgetting what you wanted to know. Okay, so feel free to do that, please. This is the outline. I hate outlines, so I'm not going to read it for you. But there is a plan. Okay, so what is information extraction? At the bottom level, the simplest level, you have a stream of data. In this case, it's human language. And you want to extract from it essential elements of information that you want to put in a knowledge base or a database. So typically, the model would be that a customer comes to you and says, I want to represent the world of knowledge in the following way, and they would provide for you the structure of that knowledge base or database. And then the task of the information extraction provider is to take the corpus stream and automatically map it to a normalized form. Well, I just said those words. The challenges are many. So you do have to normalize what's being extracted. So you have to detect the entities, the relations, the events that are being stated in human language, independent of the wording that's used. So it doesn't matter what lexical structure, what words are used, shouldn't matter what syntax is used, shouldn't matter whether it's well-formed the way a professional broadcast news anchor would use, or the informal conversation that you're having with your friend over lunch. Shouldn't matter. That's the goal. It should work for multiple languages. It should work in different genres. So we've already mentioned, for instance, broadcast news, conversational speech. We mentioned those already. Should work for newswire, for blogs, for any human communication. That's a big challenge. You need to do normalization. So for instance, if it says Michael Jordan, now you reading something about Michael Jordan would be able to know whether it's the former professional basketball player, or whether it's the well-known computer scientist, or if it's your friend who happens to live next door. You would know that. And this poor dumb machine has to be able to figure that out. Because unfortunately we don't have unique designators for who we are. Even a name like mine, there are other Weischedels in the world besides my immediate family, believe it or not. Okay, lastly, you need to do this with minimal cost, because if it costs too much, nobody's going to use it. And minimal cost means if somebody comes to you with a different knowledge-based structure than you would conceived of, you need to be able to adjust to that with minimal cost. Or a new domain, you've been working all your life in extracting information about world politics, world events, and suddenly a physician comes to you and wants to extract all the information about the medical history in the nurses' and physicians' notes for that patient. Different domain. Or a new language. So suddenly you've all your life been working in English and how would that apply to Spanish or Chinese or Arabic? So I should have had that pop up earlier, where the schema and guidelines, obviously, regarding the knowledge base are given to you ahead of time. And the approach that is the current research approach, and has been for about 10 years, is to have a learning system and use training data. So I'm told you were had a tutorial about learning algorithms, machine learning, yesterday. So you should understand now the notions of supervised training data, where the training data has been marked up manually with the correct answers by a person, or unsupervised, where there are no correct answers marked up ahead of time, or semi-supervised, where you have a mixture of material that's been annotated by a person regarding the correct answers and material that the machine is to induce without any markup. So historically, if you look at the literature, there are two really classes of community evaluations. The one that was done in the 90s was called MUC, which stood for Message Understanding Conference. So here's an example. Georgian leader Edward Shevardnadze suffered nothing worse than cuts and bruises when a bomb exploded yesterday, etc. So of course, this was an example when one was to extract terrorism incidents. And so one was to find out the location of the terrorist incident, the date it occurred, the type, in this case a bombing event, the instrument, the victim, the injury, the accused, the accuser, etc. Now, the key thing to note about this example is almost nothing here is normalized. You've gotten rid of the syntactic structure, right? So it doesn't read like English text anymore. But the only thing that's normalized is the type. This is a bombing event, even though the phrase bombed, it doesn't occur. It talks about a bombing, of course. And the date. And actually, I can't remember whether the date was normalized in the real MUC examples when I made this up or not. But that's about the only thing that's normalized, right? I mean, injury. What's normalized about nothing worse than cuts and bruises? Is the machine going to be able to reason any better about that than the text? No, because it is the source text. Okay, so the degree of normalization is something that was touched on only lightly in the research in the 90s and was only measured in the research in the 90s. And if you were to go off and do research and say, I have the best new mousetrap, I mean algorithm, it really is so much better than anything happened before, and you went and tested it on this kind of material, you'd realize you really weren't testing yourself very much on how much normalization occurred, but only on whether you can find the snippets of text having the right roles, but the snippets of text essentially aren't normalized. They're still just words, strings of characters in the language. Now, in ACE, which held sway in the 2000s, one got a little bit deeper, a little more normalization. So here's a single sentence. The founder of Pakistan's nuclear department, Abdul Qadir Khan, has admitted to transfer the country's nuclear technology to Iran, Libya, and North Korea. So one of the things is one had to automatically, by machine, mark up all the names. So you see there, Pakistan, Abdul Qadir Khan, Iran, Libya, North Korea. And the nominals, namely the descriptions. So, founder of Pakistan's nuclear department, country's nuclear technology, etc. And the pronouns, except there aren't any pronouns in this particular sentence. Not only were you to find those, but then you were to collect them together. You were to do the co-reference to show a level of understanding that didn't arise essentially in MUC. So that the founder in Abdul Qadir Khan, and he, which is, I didn't include all the sentences, right? The slide's only so large. But in the next sentence, if there's a he, the he would be connected, right? All those mentions are of the same individual. And for instance, Pakistan is the same as the country in our example here, right? The country here is Pakistan and not Iran, Libya, or North Korea. Then you are also to find relationships from a large inventory of about 24. So the start of an organization, right, and that's signaled by the word founder, and the organization that's founded is this department. And then another one is the organizational location. The department, this department, is in Pakistan. I'm sorry that I said relation for the organization start. I should have said event, right? But you can read better than I can speak. Now, I'm really going to talk in this tutorial about BBN's approach. It's not unrepresentative, but it certainly made it easier to put this tutorial together than to try to provide you a survey of all possible approaches. So the key to our approach is to regularize these into what we call proposition trees. These are predicate argument structures. The transfer is from he, and what's transferred is a technology. The founder is of a department, etc. Now, there's one other type of extraction that you read about in literature that's never had a community evaluation, right? Never had a baseline, never had a benchmark test set, never had something from which you can compare against other research papers. And that's called open information extraction. So on the level of dimensions, where the evaluation is multilingual, well, Mach was mostly English. 1 or 2 years they had a Japanese track. Only for the extraction of names, but never scenario templates, they looked at least Spanish as well as English and Japanese. Whereas in ACE, the more recent set of evaluations, Arabic, English, and Chinese were regularly tested. Now, if you can do English, Arabic, and Chinese, you could easily believe you could do almost any language, because there's actually almost nothing in common between the 3 languages. In the literature on open information extraction, it's primarily English. For entities, there are about 3 types versus 20 or so types in ACE. And in the open information extraction, at least in the literature, very little is talked about co-reference and all. So the notion of entity doesn't particularly arise, et cetera. And the key difference about relations and events is, as opposed to having an ontology, as in a very small ontology in Mach and a larger ontology in ACE, in open information extraction, the lexicon itself, namely any word in the language, which means, in essence, there isn't any explicit ontology put upon the language, but any word in the language itself can be a relation or event. So in that sense, very, very little normalization. Okay, so what about approaches? So handcrafted rules ruled in the 90s. By that we mean you, as a person, write down lots of sequences to create a finite state transducer, right? A finite state machine that maps the symbols to another set of symbols. It's the basis for virtually all commercial products that you could buy today. It requires essentially a computational linguist who's native in any language. So if you wanted to go off and suddenly do information extraction in Thai, you would have to find a computational linguist who's also a native speaker of Thai. Now, we used to do this, right? We used to do this in the 90s. And the funny thing, extracting names is really, really easy. And it was the first thing to show success in information extraction, right? To recognize a person name versus an organization name versus a location, et cetera, is actually pretty easy. On the other hand, the funny thing was, I had a person, bright young man, graduated from CMU, who was writing these patterns, and his was arguably the best pattern recognition system in the world for recognizing names in English. But for reasons I don't understand, after handcrafting these rules for about 2 years, he wanted to go back to graduate school. And in fact, it's really hard even to find people who want to do this for English, their native language, where there are zillions of them in the Boston area. And so finding them in Thai, well, it's an international city, but it's even harder. And who'd want to make a career out of this? So the sensible thing, which the community turned to, is statistical pattern recognition. And there are many learning approaches using diverse feature sets for information extraction. And which learning algorithm you use, which set of feature sets, for instance, is a large part of any research paper you'd read about information extraction. So the features can be lexical, namely they can be word-based. They can be part of speech. They can be syntactic structure, namely parse trees. They can be semantic structure, such as predicate argument structure. They can be coreference, etc. Basically, all research today uses a learning approach, a statistical pattern recognition approach. And there's one new commercial product. And maybe in the commercial arena, that'll become the wave of the future. So this is our approach. Our research system is called SERIF, which used to mean statistical entity and relation information finding. But as you can see, it doesn't roll off the tongue, so serif is a good name, and it doesn't have to mean anything anymore. It's available in English, Chinese, and Arabic. There is a name finding component available in additional languages. It's based on language-independent, domain-independent, shallow understanding. Of course, we use learning algorithms, as you might have guessed from the previous slide. And it allows easy adaptation to new domains or languages by training. Okay, so easy is a relative term. Easy compared to finding a native speaker of that language who is trained in rule writing and sits down for a few person years and creates a system. To give you an example of the kind of processing it does, at the bottom we have a long president, Yugoslav President Slobodan Milosevic, received on Thursday the representatives of the Association of Yugoslav banks, et cetera, et cetera. So one of the easiest things to do is to recognize the names. So here I've annotated the names for you, right? GPEs, geopolitical persons, organizations, et cetera. Here's the parse tree. So you can see the, and then the name of the organization is an NPA, a noun phrase, base noun phrase. That joins together with the comma and this verb phrase, right, a reduced relative clause, to form a larger noun phrase. And adding on the comma and a relative clause, we get the full noun phrase, which because of the of, it becomes a prepositional phrase, etc., building up the top, the sentence level. So the parse tree simply puts together the words into meaningful phrases and more meaningful phrases, etc. This is the co-reference level. So we've identified that this Association of Yugoslav Banks is the same as its, that Milos is the same as the who is the same as the general director, etc. And given that, one can associate the predicate argument structure that comes from nouns. President of Yugoslavia, right, etc. And from the verbs, right, so Milosevic received representatives, and so on. So that's the level of linguistic analysis. Okay, so this is purely linguistic analysis. No normalization has happened, right? It's still the words of the author. Okay, so the normalization happens after we've done all the linguistic analysis to say, this is the sentence structure, this is what the sentence means, here are the predicates, here are the arguments, here are how the phrases refer to each other. And only then do we do the normalization step for the customer's database structure, the customer's knowledge base structure, the customer's ontology, or in other words, the customer's formal view of the world. Okay, let's look at names. Names are really easy, so that's a good thing. So here we have a long sentence, and the names are marked up as the locations, persons, organizations. Up to 1996, there was no learning approach that was competitive with hand-built rules. Since then, statistical approaches have achieved the state of the art and are what people use. There's still commercial products that are based on handwritten rules, but that's not where the research is. That's not where the new generation of technology will come from. Turns out BBN was the one that achieved the first state-of-the-art performance in numeric addition by learning algorithm. And also, you can get good performance even on pretty bad input. So automatic speech recognition generally produces imperfect text. I'm going to show you a slide of performance later, but here was the original structure of the algorithm, the original algorithm that achieved state-of-the-art performance. And the goal was to have one language model for each category that you were to recognize. Okay, so this was in the days of muck evaluation, so there were persons, there was organizations, there were 5 other categories, and one for everything else that's not a name. And then you simply march through the sentence, going through this finite state machine till you get to the end of the sentence. And you assigned bigram probabilities. I don't know whether you can read this, but for instance, from word 1 to word 2 to n, for instance, you look at the probability of the current word given the previous word and the name category, person. And the same as you march through all the states within this region. The same here. And then there are transition probabilities from one region to another. So for instance, the transition probability, which again you may not be able to read. Sorry about that. The probability of the name class, the current name class, given the probability of the previous name class and the probability of the previous word, times the probability of the word given the current name class and the previous name class. And so you just followed all possible paths given a sentence through this finite state machine and selected the path probability that gave the maximum probability. Now the nice thing is, since the speech recognizers also use similar models, you can actually combine the probability of the output names given the acoustic signal quite straightforwardly, and you get a result such that the error rate given a speech input is essentially approximate, as you can see from these dots, essentially approximate to the error rate if you had text plus the word error rate in speech recognition. Okay, so it degrades very gracefully, right? As the speech recognizer becomes more effective, therefore the word error rate goes down, and therefore the overall performance goes up linearly. Okay, so much for names. We'll go back to it later when we talk about how to reduce the amount of training data required. So for entities, I think I've covered everything here, so I'm going to skip this slide. At the moment, the ACE evaluation used 7 types: person, organization, geopolitical entity, facility, location, vehicle, weapon. Here is a color-coded markup for Irish Prime Minister Brian Cohen. Met yesterday with EU leaders in Brussels. He returned home to Ireland today. So you'd like to get that the Irish Prime Minister Brian Cohen, where Brian Cohen is the head, is the same as the Prime Minister, is the same as the he, etc. So that's what you'd like to be able to do. If you can do that, then we go on. So here's another example sentence, again with the markup. It's not crucial. And if you can do that, if you can make the entities, one way to do that is say, you have names, we found them already. Remember the diagram, whatever thing was flowing down. You have the descriptions, you have the pronouns, where's my cursor? You have the parse trees. You have the predicate argument structure, right? I showed you that in the previous slide. You have all that as features to build on, right? Then you can have a model that learns how to predict coreference given those features. You can predict relations given those features. You can predict events given those features. And then you just merge all those results to produce the output, namely the entities, the relations, and the events. So I'm going to walk through those 3. So for instance, if we're midway through a document and we've already decided that entity 1 contains these mentions, right, which might be a name, which might be a pronoun, which might be a description, and entity 2 only includes 1, and entity 3 includes 2. So we've worked through the first 6, and we're at the 7th way through the document, the 7th mention of a noun phrase. So we extract the features of mention 7, and we look at the features of each of the mentions of the entities, and we make a prediction, given our learning model, right, that mention 7 is associated with entity 2 with this score. Mention 7 is associated with entity 3 with this score. Mention 7 is associated with a new entity, never seen before yet in the document, with this score, or with entity 1 with this. And of course, the highest scoring one is the decision we will choose. I think, in the interest of time, since I'm running a little slower than I expected, I'm going to skip the pronoun coreference model. It's not complex, but basically one decides the feature templates, here's an example of them, and use the model to predict which is the most likely referent for the pronoun. Let's go on to global entities. So that was all for linguistic coreference, right? In a document, does he refer to this character or this character, etc. Now suppose you go to the Michael Jordan problem. Which Michael Jordan is it when you see a document that mentions Michael Jordan? So one of the things that we have to account for is name variation. So here are a lot of name strings: Abu Abbas, Abu Mazen, Adam Smith, A. Smith, Andy Smith, Mahmoud Abbas, Muhammad Abbas. So those are just strings. They've been identified as names. In fact, they've been identified as person names. Then we produce a similarity score between any pairs of names. So I'm not going to explain why at the moment. These don't look very similar. But you could imagine there might be world knowledge that we can know that there's a 0.9 probability that Mahmoud Abbas links to Abu Mazen, even though they don't look at all the same. And the same about Muhammad Abbas and Abu Abbas and Mahmoud Abbas and Muhammad Abbas. Then, given those scores, we build clusters of these document entities. So we've got this name similarity, and we see a document with an entity 1, and we see a document with an entity 2, and we start to cluster those document level entities together. So for instance, here are the name strings, and here we've made some decisions, right? So Abu Mazen as a document entity, Abu Abbas, a different document, Mahmoud Abbas, a different document. These are document entities. And for each name string, we collect a set of equivalent names. We collect all the entities that include any of these name strings. And lastly, we do a agglomerative clustering, right? So we start with singleton clusters, which you have here, right? 3 singletons. Merge the clusters using evidence from name variation, from what knowledge we've extracted from the documents about the entities mentioned in each of them. Web knowledge, such that in fact Abu Mazen is another name for Muhammad Abbas. And we stop when no clusters meet the threshold for merging, right? We stop before we create gibberish that everybody is the same. And so in the end, the ideal would be that Abu Mazen is the same as Mahmoud Abbas, and Muhammad Abbas is the same as Abu Abbas, but they're very different leaders. One is a Palestinian leader, one is a convicted terrorist. So that's the challenge, right? So I told you about the Michael Jordan challenge. The other challenge is when the names don't look the same. They aren't spelled the same, but they do refer to the same individual. So there's lots of knowledge that can be brought to bear. The structure of the diagram, well, it's complex. So let's just look at the words. So the input is SGML. Serif has run over all the documents, so you know the entities, you know the relations, you know the events that are stated regarding each of the individuals in the corpus. You have world knowledge. So from world knowledge, right, from the web, you may know that Mahmoud Abbas is the same as Abu Mazen. There are spelling variations that you can draw on by simple algorithms that says that this spelling is actually a different spelling for the same organization. Now, this particular organization, it's estimated there are 30 different spellings that typically appear because it's an Arabic name and there's no regular way to transform an Arabic name into an English spelling. Another fact is features. The most obvious feature, of course, is about persons, is gender, et cetera, to use. And then there might be additional knowledge, right, that this Michael Wynn is an Air Force secretary, this Michael Wynn is a prosecutor. Do you have enough knowledge to suggest that maybe these two are different people? And then you produce as an output the particular ACE program format, APF. The name matching is easy to explain, so let me just tell you a little bit more about that. So there are simple algorithms to recognize misspellings, alternative spellings from transliteration, for instance, an Arabic name being rendered in English. There are aliases such as Mahmoud Abbas and Abu Mazen. There are acronyms so that you know that IBM is the same as International Business Machines. Though that can get you into trouble because BBN is no longer an acronym for anything. It's just as SRI, I think, is no longer an acronym for anything. And there's name variation simply because we can use short forms. So the world knowledge is derived from the web. So, for instance, Wikipedia is a good source of aliases. There are other sources, so you can find geographical databases to find out how many Springfields there are in the United States. Then there's ways to compute the similarity, as I already mentioned. So, in interest of time, let me skip this. Then there are ways to disambiguate. So the Michael Jordan case, right? So you can use the titles or descriptions of them. If they are consistent, then you have reason to believe they are the same individual. And if they are inconsistent, right, or the ACE relations are inconsistent, or the events are inconsistent, you have evidence that you have different Michael Jordans. Again, you can draw on world knowledge. So Wikipedia is a strong resource, again, for English to do that. And then there simply is a document metadata that you can use as well. So, for instance, if someone is mentioned as president in 1980, actually, let's make it a little more real. Someone is mentioned as president in 1991, and someone with a similar name is mentioned as president in 2003. You know they're not the same president because of term limits. Okay, so sorry I rushed through that, but there's several other points in the outline. Now relations get to be more interesting, right? The names have the nice property that the strings, they're just strings, there's no structure. When you get to coreference, you have to take two strings and say they're the same. They're referring to the same thing, right? So that's a harder problem, right? Any pure sequence of tokens is an easier problem than connecting two tokens. Now with relations, you have even more problem than coreference, right? Because you have to identify two sequences and identify how they're related, if at all. So now you have to make three decisions. This is interesting, this is interesting, and they're related in the following way. So ACE is a good way to look at relation normalization. Here is a list of them all. So who employs whom, what organization employs whom, ownership of things, the founder of an organization, etc., membership in an organization. Then they're physical or spatial, if you prefer, something being very near something else, or a person or an organization being located at a particular location. Part-whole relationships, personal or social relationships, so familiar relations are obvious to everybody. Someone having a lasting personal relationship with someone, for instance, being a partner. Business relationships, so one organization having ties to another organization. In the agent artifact area, there's only one, as you can see, user, owner, inventor, or manufacturer, right? So a person or organization related to a thing, right? User, owner, inventor, or manufacturer of something. And then lastly, the two general affiliations. So this is the ontology, right? They're grouped together, so the top 7 are all kinds of organizational affiliations, the bottom 2, general affiliations. Pretty shallow ontology. Not interesting as an ontology. But you can see you have to make several discriminations, right? So there's just under 20 relations there. So to extract relations, remember I said assume that we already have done the name recognition, the recognition of descriptions, the recognition of pronouns, the recognition of the parse tree, and the recognition of the predicate argument structure. So then those are all features that one can use in extraction, right? So you want to connect two entities, right? The employer of an employee, right? Or somebody being the spouse of someone else, or someone being located at a place. So an example would be Irish Prime Minister Brian Cohen met yesterday with EU leaders in Brussels. So there are two relations there, right? Irish. I know that may sound funny, but in ACE this is well defined. Irish is intended to be the government of Ireland, employs Brian Cohen. And Brian Cohen is located at Brussels, and the time frame of the report was noted yesterday. So the interesting factor, at least in English, and I don't have the statistics for Arabic, for instance, but most relations are expressed in a single phrase, a single syntactic structure. So, in fact, that was so true in the ACE world when one tried to, it was very hard for people to mark relations that went across sentence boundaries. And it was so, the human performance of that was so erratic, it was simply eliminated from the task. And so it's a powerful feature that you can look at the syntactic structure to help you get the relations right. So French president, that's a role management relation. Nicolin arrived yesterday from Moscow. That's a location relation in a clause. His trip to Israel, right, in a single noun phrase. You're getting the relation information. That makes it much more tractable than if you have to combine the information across sentences. Now, you still have to do co-reference, right, because you don't know who he is. And to get it right, you have to identify who he is, right? So first identify the mentions, as I said. Classify the mentioned pair as either one of the inventory of the relations or no relation holding between any pair. So we use predicate argument structure as crucial features for this, namely the logical subject, the logical object, pre-modifiers for nouns, and the object of a prepositional phrase. By logical subject versus logical object, right, let me just make clear, if it's not obvious to you, I simply mean that if you say John ran the meeting was run by John, in both cases, the logical subject is John, even though in the second one, the syntactic subject is the meeting, right? John ran the meeting should be the same as the meeting was run by John. And in the predicate argument structure, they should come out as identical. Okay, so that's what I mean about logical subject, logical object. So examples are the French president. The predicate argument structure is president has a pre-modifier French. Ivan went to Moscow. The predicate argument structure is that the logical subject of the went is Ivan. And there's a prepositional phrase to Moscow. Ivan arrived at a meeting in Moscow. There's a logical subject. Oh, I'm sorry, Ivankov, rather than Ivan. Poor Ivan. And he's at a location which is what? A meeting in Moscow. So then one can have feature templates that are used for the extraction process, right? So suppose the feature template is arg1 is of type X, arg2 is of type Y, and it's a proposition Z, which for Bush in Washington would be arg1 is of type person, arg2 is of type GPE, and the proposition is in. If so, you produce the located at relation. Okay? So how do you have a learning model for this? Well, you have annotated data that says for Bush in Washington that the relation is located at, and the person, the first argument is Bush, and the second argument, the location, is Washington. And from that annotated data, you simply estimate the probabilities for all the features and run it through your favorite learning algorithm to make the predictions on new data where it isn't marked up. Another example is for things like the Canadian businessman, where you have the pre-modifier. So if the argument 1 is of type X and the argument 2 is of type Y, and the proposition is a pre-modifier arg1, arg2, and the head word is W, So here, in the Canadian business, and that's that becomes argument 1 is type GP, the argument 2 is type person, the argument 1 head word is businessman, and then the relation is citizen of. Again, you estimate the probability simply by looking at the supervised training data. And then when you decode, you look at the features, and the model tells you the probability. Okay? Now the ACE event inventory is richer. So again, here we have the one level above the base types of events, right? So they're life events, they're movement events, business events, conflict events, etc., through justice events. And here are the events to be recognized, like born, married, divorce, injured, die. And justice events, arrest or jail, release or parole, trial or hearing, charge or indict, sue, convict, sentence, etc. So more than 24 types of events. So there's a fair amount of discrimination here, right? You have to distinguish more than 24 types of events. But there are all kinds of events that aren't covered here. So, for instance, anything about sickness, disease outbreak, simply isn't covered. So the key thing, again, to remind you is, in information extraction, the model is that the customer has some ontology. The customer has some set of events types. The customer has some set of relation types. The customer has some set of entities. They may not be ones we worked on before. They may not be ones you work on. And given some markup of human language, given that ontology, you were to learn how to extract the information to put in the customer's knowledge base. So this is the inventory in ACE. So if you want to do research, I would heartily urge that you always compare to a baseline on a standard test set, like ACE or MUC, and report your results. That's the only way to know that you've done something better. You can know you've done something cool without ever making that comparison. But I would claim it's not cool unless it's better. Okay. So, for those events, detect and classify the events is the goal. One of the crucial items is the nice thing about events rather than relations is that there's oftentimes a trigger word. A word that, it's raising its hand and saying, I'm here, I'm an event. Can't you see me? Right? That's the notion of a trigger word. And there may be 0 or more entity arguments. So here's an example. Irish Prime Minister Brian Cohen met yesterday with EU leaders in Brussels. He returned home to Ireland today. So I've underlined the trigger words. Met is clearly a trigger word for a meet event. Return is clearly a trigger word for a movement event. So the arguments happen to be, in the case for the meeting event, right? Brian Cohen is one agent, EU leaders are another agent, and the time is yesterday. These are just the strings. Of course, yesterday should be resolved to a real date, normalized to a real date. The transport or movement event is he is the agent, the destination is Ireland, and the time again is today. Again, you want to normalize the today to a real date. And the he we get from coreference, right, which we already talked about. So events actually turn out to be easy to explain, right? The key is first identify the event triggers, such as bombing, conviction, blew up. So bombing and blew up are good triggers for the same type of event, right? An explosion event. Conviction is a different kind of event, a justice event. Given that you believe there's an event there, right, because you've seen a trigger, attaching entity and value arguments to the triggers is the key thing. So the bombing in Spain, well, that gives you the location. His conviction last year, that indicates who was convicted and when it occurred. 2 people died when the building blew up. Okay, so building blew up, it tells you the object of the explosion event, and 2 people died is telling us the victims.
I have a question.
Yes, yes.
Does the word build trigger an event or not? Like, why building is not an event? Like, how can you resolve this ambiguity? Like,
So I can tell you the way we do it, right? So some people would argue that building has 2 different senses. One, the construct, right, that is a physical object, and the other is an event, an activity. That's one way to do it. And to do that, you need some large sense inventory and some annotated data to discriminate which of the 2 senses of building it is. We don't do that. We simply believe that the words are disambiguated in their context, which seems reasonable enough, and we don't care what the artificial inventory is. We're not going to create one for this purpose. And so in the context here, right, blew up is the main predicate. Building is one of its arguments. There's nothing around building to indicate that there's a builder, there's something being constructed, and so that sense just is never seen in the pattern that you have some physical object that's exploding is seen. Did that help?
yeah, but you mentioned earlier that you look for the triggers, like.
So building would be identified as a trigger.
But
It's just it would fade away because you find no arguments for it, and its role is that it's the argument. It's not a main predicate. Good question. So actually, I was elaborating. I didn't realize it on the bottom note. Right, these actions are not independent. Right, you want to propose lots of trigger words, lots of possible events, and you want to eliminate the ones that don't make sense. And this is how. So there are really 3 steps: proposing triggers, proposing arguments, and coreference. So to do the argument attachment, you have to attach it to something. That means you depend on the triggers. To do the event coreference, you have to have a set of event mentions, meaning a set of places where the triggers occur, and the arguments. But there are the independencies. So as I was saying with the building example, you want to associate the arguments with the triggers. You have to resolve, for instance, whether there are 2 bombings or 1 bombing and the consistency among them. And so you prefer triggers where everything comes out consistently, right? And coming out consistently, again, is all computed as a score. Okay, so I've said points 1 and 2 already. Point 3, filter and combine trigger argument clusters. Hit a home run has no target, namely hit might be a trigger for a relation word of interest, but home run is not an argument of interest. And so it would be marked as not an event. So made a call. The problem with made a call is, right, the real trigger is call, and the made is just a support verb because you've stated the event by a noun, right, call. And so you need to collapse all the do support words like made, do, etc., and take the noun as the trigger instead. Okay, so I should point out that not all these tasks are equally easy. So, for instance, for humans, the interchanger agreement on marking up names is about 97%, right? You take two people, you mark up names. Assuming they're fluent in the language, you get about 97% agreement. For co-reference, the agreement for entity recognition in ACE among humans is in the 80s. For relations, if I remember correctly, it's a little below that, so let's say in the 70s. For events, it kind of falls through the floor. So 60% is about the best you would remember. So I'm sure, going from memory and not having to look this up in the last week, those numbers aren't exact. But the relative difficulty in humans marking up the data is there. Yes.
That was within .coref, or that was the...
That was within document. I don't know the numbers. Maybe Jim knows the numbers on cross-document human annotator agreement. Okay, so that's sort of the basic framework. But the real name of the game is now, in research, is minimizing the cost. So a customer comes to you and says, I have this great knowledge base I'd like to fill automatically. Let's say it's about patient records. And you don't have a clue about the ontology of medicine and indicators of problems and drugs. But they have an ontology, and you say, oh, take me 25 person years and I can do this for you. Okay, well, it's probably not going to happen, right? I mean, they need it sooner than that. So what do you do? Okay, so that's the most active area of research, I would say, now. So one area may not sound like it's directly relevant, but it's creating resources beyond tree banks. So I don't know whether your machine learning talk yesterday talked about the notion of automatically learning to parse from marked up data. But the training data, the supervised training data, is called a tree bank. A collection of parse trees. So one of the active areas is to go beyond tree banks. And BBN and its collaborators at the University of Colorado, the University of Pennsylvania, and USC's Information Science Institute are creating a resource for that called OntoNotes. It's to be a skeletal representation of literal meaning. And what we had before we started was text being marked up as a tree bank and propositions. This core existed. And what we're adding is word senses and co-reference to create a unified database of annotation that includes, yes, parse trees, which is what everybody's been using since, let's say, 1995 for English. Predicate argument structure, co-reference, and word sense. Creating an integrated database. Now, one of the problems in creating annotated data, particularly if it's going to be a resource that you want the world to use and you want to drive learning algorithm research, is you need to find a sweet spot so that the inter-annotator agreement is high enough. So the rule of thumb is that if human performance is at n%, machine performance is likely to top out at n minus 10%. Okay, so sometimes you do a little better than that. But you shouldn't expect it to be better than 10% loss. So that means, as it turns out, it means our target is 90% agreement in human annotation on all these areas, right? It's true about tree banks. It's true about proposition banks. With co-reference, we're not quite at 90%. We're in the mid-80s to high 80s. And word sense annotation. So we're achieving that goal. there. Productivity means, well, if you don't have enough training data, you don't get very good performance. So for instance, in parsing, everybody understands parsing because we've, people have worked on it with good tree banks for 12, 15 years. 100,000 words marked up by trees, it doesn't give you very good performance. 250,000 gets you up to a baseline. Going to 1 million words, you're still getting far better performance. So productivity, namely the volume of data you can mark up, is crucial. And lastly is the depth of representation. So as an example, if you make your word sense inventory too fine-grained, people won't agree very well, and the inter-tiger agreement will suffer. On the other hand, if you make it one sense, there's nothing to do. So our goal has been to find a sweet spot there, and we spent at least a year doing trial annotation and measuring all, what was the inter-tiger agreement, how quickly could we do it, and adjusting the depth of representation accordingly till we achieved the goals of 90% here, 90% for most of the words here, not all of them, and mid-80s for coreference. Well, the good news is that you can get hold of this data, right? You can get this data from the Linguistic Data Consortium. Release 2 of Ontonotes was made almost a year ago, and release 3 will be out by the end of the summer. So that's a new resource. What does it look like? Actually, it looks kind of unreadable. But it's a database, an integrated database of parse trees, coreference. So E2 is coreferent with E4, and E2 is coreferent with E7. Here we have the predicate argument structure, and down here we have the ontology. For that sentence I showed you before, the founder of Pakistan's nuclear department, Abdul Qadir Khan, etc. And the interesting thing, if you are not English-centric, is the data is released in English, in Arabic, and in Chinese. So you can do the work multilingually. Well, okay, so that's one way, one active area of research. So this is generic. It's not specific to information extraction at all. Another way is semi-supervised learning. So people have been working on this for a long time. Let me show you a little more detail here. Again, it's about names. Names are so easy to understand and so easy to make progress. It's the first where people made progress in this area of machine learning. So semi-supervised learning, to remind you, is you have some amount of manually marked up data, but it's small. And you have some amount of unmarked data, and you want to capitalize on that so that you don't need to mark up so much data. Now, in particular, the experiment I'm going to describe was done by Scott Miller, who's not in the room, but is in the COE summer activity. So Scott invented this about 5 years ago. So it involved clustering of words. And I'll show you what that means. And it involved active learning. Namely, the learning algorithm says, I have two cases that are so close together, I can't make a reliable judgment. And you provide that case to a person and say, okay, I'm really confused about this. Can you tell me which is the better one? And that's called active learning. And you just do that iteratively, where the machine asks the person for the most, for the cases that it's most confused about. And I'm going to go on and tell you last, as the third point, is about iterative learning. So what does the context-based word clusters mean? Well, you take a very large corpus, tens of millions of words of the language. And this is an algorithm that was invented at IBM around 1990. I don't remember the exact date. By a strong team at IBM at the time. And so this is what it does. It basically looks for the words that are most similar by who its neighbors are, right? So basically it just looks at the previous word and starts to cluster the words by who its neighbors are. So as you notice, discussion turned out to be similar because it shared prior words with conversation very closely. Opinion came out to be close to understanding. Assessment came out to be close to evaluation. Analysis was joined in as closest to evaluation assessment. Conversation and discussion were the last to be entered in. And then, based on which path you take in this tree, from the root to the edge, you get a binary string. Okay, so they all start with 1 here, right? And if you go this branch, you have 1 in the second position. If you go this branch, you have 0 in the second position. And you get a binary string that indicates which cluster you're in. But notice it's a hierarchy of clusters. So Scott's idea was to use 100 million words and to run the clustering algorithm over them. And I just showed you this part of the build process, right? And the point is, you get some interesting clusters. So these pretty much look like first names, right? These sort of look like occupations, except it makes some funny things. Who knows why slang is there? But in terms of its neighbors, it makes some errors. But on the other hand, there's some really interesting clusters that come out. And notice it's a tree. So you can choose the level of granularity you want. You can be really fine-grained. I want things that are only very similar. Or you can move up the tree and take things that are a little more forgiving, less close together. But they're closer together than the other things. So this provided an automatic way to smooth the probability models. It provided an automatic adaptation technique. It provided automatic discovery of relations. And it provided automatic induction of frames and argument structure. The bottom line in the performance is, here's that first hidden Markov model that I showed you about recognizing names. So this is a log scale, 1,000 words of training data, 10,000, 100,000, a million. A million sounds like a lot, but actually for names in English, you can get a million names with 200 hours of annotation. That's just 5 person weeks. And here's the F measure on name recognition performance on a single test set. So you notice it goes up, but it's not going up linearly at all. It's going up slowly. Here's the result of his experiment in semi-supervised learning. It went up dramatically before it tailed off. So at some point, you can't believe the curve, because this was simulated active learning as opposed to real active learning. Namely, we never had more than 1 million words of marked up data. So instead of having, as you'd like in active learning, several order of magnitude more data to draw from, that's why it tails off so rapidly at this point. So you can't believe the upper part of the curve for the active learning part. Interesting facets, right? So the HMM, which is a generative model, if you move to a discriminative model, you actually get worse performance, right? Might be counterintuitive to some people, but that was empirically what we found. The interesting thing is, though, if you add the discriminative model and the clusters, right, the word clusters, you get a uniformly better than the generative model. Uniformly better across all points. That's interesting. So that means that boneheaded way where I say, this word is similar to that word because they share this previous words a lot. The distribution of previous words is similar. Sounds kind of boneheaded. Why should that make a difference? But in fact, it makes a distinct difference that you are able to generalize by who your neighbor is to data you've not seen before. Well, then the active learning helps even more, right? So here was the discriminative model. Here's the active learning. Here's the discriminative model with the clusters, right? So the clusters gave you more bang for the buck than the active learning did. But if you put them all together, it's additive. So these were all experiments in English. Tried the same experiments in Arabic. So that's the hidden model, Markov model curve. Here's the approach with the discriminative model, the clusters, and the active learning. Notice you get a 25% reduction in error, even at maximal training. And if you look at this error bar, which is about 89% performance, right? You can get to 89% performance with 1/5 of the training data. Okay, so that's where everybody should start to pay attention. If you can cut the cost, right, the manual markup, by a factor of 5 or 10, you've actually done something pretty significant. Well, a different approach that we're just starting on is called iterative learning. Historically, it goes back to a seminal paper by Ed Hovey and I'm blanking out on his first name, but Ratnaparky is his last name, where they had this idea, right? It was to do simple-minded question answering, like when was Mozart born? There's a single correct answer to when was Mozart born, right? Unlike certain people who give lots of different birth dates to hide their real birth date. And the simple idea was, when was Mozart born? I could find all the ways that is ever said, because I know if I know the birth date of Mozart, and I know all the ways his name is said, I can just search the web for all sentences that include that birth date and include Mozart's name. And I can just memorize all the words that occur between those two endpoints. And I can have a learning algorithm that brute force learns the ways that one can express birthday, right? Forget about Mozart. After you've got all these strings, forget about Mozart and forget about his birthday. Use those strings, all those intervening strings, as a way to learn how birth date is expressed. Okay, so that was the seminal idea. So now let's generalize on that and say we want to deal with lots of kinds of things. So the generalization is a pattern database. You'd like to build that. And you have proposed pairs like Thomas Edison and the light bulb, Alexander Graham Bell and the telephone, Benjamin Franklin and the lightning rod. Okay, and obviously we're thinking about learning invention, right? So you retrieve from the World Wide Web or any other corpus. And what do you find? You find instances like Edison invented the light bulb, Bell built the first telephone. Note that's a much different way of saying invention, not one I would have thought of. Edison was granted a U.S. patent for the light bulb. Another way that I would not have automatically thought of as saying invent. Franklin invented the lightning rod. And then suppose you induce patterns. Now the original work from a few years ago, as I said, was simply memorizing the words. Okay, well there's a hazard with that. You get extremely high precision. But suppose the author, uses slightly different wording. Suppose when you talk about something, suppose I say Miller built recently a better such and such, right? Well, it actually is talking about an invention, but notice I put in the word recently, and instead of first I said better. Well, unless everything in the world that's ever going to be said is in the web, you're not going to get it, right? So your recall is going to suffer, but your precision will be great. So instead, one thing to do is generalize, right? So here we're generalizing into predicate argument structure, right? And saying, well, granted is one thing. The indirect object is an inventor. The object is patent for invention, right? So we're looking at Edison was granted a U.S. patent for the light bulb. So notice this generalizes away from a lot of those details, right? It captures the main predicate, granted. Captures you want to see an inventor, right? Namely a person, as the indirect object. You want to see patent, and you want to see the thing that's being invented. And you prune from that set of examples, and you add to the set of examples to your pattern database. And then you say, gee, it worked once. Why don't we try it again? Okay, so this is one of the really promising areas of research. Perhaps the best work to date where you're actually memorizing the strings of words is at Carnegie Mellon with Tom Mitchell and his students. So don't remember the website off the top of my head, but he's actually making, he's actually publishing what they're discovering by this technique, instead of using, in fact, this deep analysis by simply memorizing the words between the pairs. And he's added something more powerful than this diagram, right? So imagine that there's another loop over here. So here we're trying to learn the way invention is stated. Suppose you're learning a way over here, the object categories for inventor and invention, which their group is doing. So there's a lot of promise here. Lastly, let's wrap up. What can you use it for? Okay, so I have a clear bias. I have since I was in graduate school. The papers are nice, but what do you use it for? Does anybody care? Could this possibly help anybody's life? Well, okay, those are deep questions. So, but if you can at least talk about applications, you can make me feel better. So the notional idea here is you have all this human language, and there are all ways it comes into play, right? And information extraction, what does? Names, entities, relations, events, puts them in a database or a knowledge base for you. So what could you do? Right? What do you do with this database? I don't know. But for instance, you can produce tables of information, employees and employers. Okay, well, tables actually are pretty fundamental, and we use them all the time to communicate information. There's a notion of link analysis, social network analysis, that you can use. You can from the events, you can produce timelines. Okay, so timelines must be important, or people wouldn't produce them all the time. In our culture, right, it's pretty fundamental. That's the way we think of life, is through timelines. You can have geodisplays. So there are lots of ways to present the information, and if people have information and they have appropriate displays, whether it's tables, graphs, timelines, or geodisplays, they'll use it. Here is an early demo we put together to have show the value of a knowledge base. So here, this is really old, of course, as you can see. And I guess you can't read it. I'm sorry about that. Let's read the screenshot. So we put in the search term chemical Lee. These are all the documents that were retrieved, simply finding wherever chemical Lee is mentioned. And I mean literally the phrase chemical Lee mentioned. But the knowledge base behind it says, here are various descriptions of the individual who was known as chemical Lee, right? Iraqi general, commander, Saddam's cousin, etc. And here are relations, again, in the knowledge base, but written out in an English form. Ali Hassan al-Majid works for Iraq. That was his full name, Ali Hassan al-Majid. So the knowledge base knew that, right? It had learned that from the corpus, etc. And here we've selected one. Can I read it for you? Yes, the bottom one, which you probably can't read. Where's my mouse there? Ali Hassan al-Majid is a member of Revolutionary Command Council. And so if you selected that, you would get the document that stated that and highlighted the phrase that led the system to believe that. Right, the evidence for the relation. And lastly, it would list out all the entities mentioned one by one, including repetitions of the same thing. So you could select any one and find in the document. So this is for the case where you want to find information about, for instance, an individual, organization, event, etc. In this case, it was information about chemical Lee. It rendered in a prosaic English the various knowledge it had, and you could go back to the source documents. Here's another example, again associated with documents. The goal is to provide a user with efficient access to a large amount of information. Find it all, independent of whether it was written in Arabic, Chinese, or English. Provide it in English. Compress redundant facts so you don't see the same thing over and over again. Resolve pronouns and dates. So again, I'm afraid you probably can't read this very well. So this highlighted part is redundant information with the one above, right? So someone happily, before they took the screenshot, pressed this little button here saying expand this one, and notice the one below it, number 2. There are 7 different ways that this fact is stated, and we didn't expand that one. because the user needn't see it all. And notice the source language for this was in Arabic, and this is the machine translation. Pronouns are helpfully converted to what the system believes the pronoun refers to. So the he is Bernard Kouchner. And dates are resolved. So this next week is 2005, week 44. Or Friday is 2007, 0601. So an example of this is if you, we did this a while ago. We typed a query to Google saying Abu Abbas statements hijacking. So we wanted statements by Abu Abbas on hijacking. We probably should have put the by in, but and Google found 50 documents for us, none of which were statements by Abu Abbas. Rather, they found lots of statements about Abu Abbas, who's well known for hijacking, famous hijacking. On the other hand, our system, using this predicate argument analysis, found in the top 5, found the first one relevant. Second one was a miss. The third one was probably relevant. Fourth one is relevant. The fifth one is not relevant. So again, we're getting essentially 60% precision in the first 5, whereas Google was getting, in the first 50, 0% precision. And the key thing is that identifying the entities, relations, events, predicate argument structure of everything in the corpus, and matching against the predicate argument structure of everything in the query, find statements made by or attributed to Abu Abbas on hijacking, is what made the difference. So come to the end, actually pretty much of the time, as well as the end of the slides. So if there's a quick question, I'll be glad to answer it now, and if not, I'll be glad to answer questions during the break. Yes?
I hope it's quick, but for much of what you described, you have a sequence of steps, and in each step you have some error that's introduced. So by the time you get to something like the later stages, you have these cascade errors.
Yep, yep.
Is the field moving in a direction that can avoid those cascade errors, or will you always get error, or what do you recommend?
So that you're certainly right, Jim. That's an active area of research. What we do is pretty much a heuristic. We can generate more than one parse. Generally doesn't help, and so we don't do that at this point. But the capability is still there to generate more than one distinct parse and use it. The same thing is true about relation and coreference. So there's an issue. Do you want to know the coreferences before you do the relation extraction, or vice versa? So what we do there is we actually hypothesize relations without doing coreference, do the coreference, and then redo the relation hypotheses, re-ranking them based on. So these are all heuristics, as opposed to, and almost everything we do is a greedy algorithm, as opposed to a more exhaustive search or a joint search. That's usually true. And I do that basically without apology. We're engineers. You could take any component of our information extraction system and find a better one. Whether it's the parser, the coreference, the predicate argument structure, I bet you could find a better one. But assembling them all together, this Serif system has, certainly for the last 2 ACE evaluations, and deeper than that, longer than that, it's just I don't remember, it has come out first essentially in every dimension in overall scores. So we would love to have a better parser. We would love to have better coreference, and we have to use our resources accordingly. The biggest errors by far, and the ones we do focus on, for instance, are errors in ASR, in speech to text. for which there's no recovery. And so one of the active experiments we'll be running in 2009 is a way to deal with, for instance, person names that are out of vocabulary. So I believe IBM and SRI have done prior work in that area. And that's a killer. Or because if you don't see if it's not in the vocabulary of the speech recognition system, you're never going to see the name. You're never going to be able to distill the information. Same sort of problems with machine translation errors. We've done some work there. You know, you'd like to do joint optimization, but for engineering purposes, with a system this complex, you know, our real customers want us to be able to process 50 megabytes an hour. And we can do that. Actually, we can exceed that. I don't know what that is. That's, let's say that's 1,500 words a second. I don't remember the exact numbers. That's blinding fast. And we have to try to maintain that. I'm sorry, that's probably more than you wanted as an answer.
No, I thought it would be interesting to hear.
Yeah. So we take a definitely a very engineering approach, namely the overall system accuracy and speed. You're absolutely right. Cascading errors are a serious problem, but there's some cases where it's much worse than others, like the output of MT and the output of speech to text. Yes?
Is your software public?
No. No, we're a company, and this is on a path to being a product. On the other hand, with allied researchers, we do make trained executables available to allied researchers at no cost. So Jim, who just spoke in the center he's in, used our Arabic version of Serif and our English version of Serif in their research last year, and I hope this year. So basically, we do make it available to partners at no cost. Good question. Any other questions? Actually, I'm not sure of any open source information extraction software except the very old pattern-based techniques that's available in Gate. Is anybody?
There's some name finding things, right?
Oh, yeah.
Name pipe.
Yeah, but a name recognizer you could do yourself in no time. There are lots of open source components, right? And there are at least 2 or 3 excellent open source parsers, for instance. Pardon? Really? Okay. But you are right. There's, if you search for NLTK on the web, which probably spells Natural Language Toolkit, and you search for the name Loper, L-O-P-E-R, you should be able to find a pretty interesting natural language toolkit that should be open source.
All right, let's thank our speaker.